Ignore the white boxes, please. So the next one I'm going to talk about here is 4 electron domains. And as we talked about one of our first shapes here, that shape is a tetrahedron. So the electron domain is going to be tetrahedral. The molecular geometry, now in this case, we have 3 options. Option 1, methane, CH4, is an example for that. And it kind of looks like this. And the molecular shape in this case is the same as the electronic geometry, namely tetrahedral. But another possibility, I'm sorry, and so all these bonds are the same, so they're all 109.5 degrees. Another possibility is ammonia, so a weak base, very common cleaning product, often used in smelling salts if you pass out. And it has 4 electron domains around the center atom, the nitrogen, except that 3 of them are shared pairs. One of them is an unshared pair. So what would that look at in space? Well, it would look something like this. And again, you want to think about the shape that the atoms themselves, so look at where the letters are. Ignore that lone pair, that unshared pair right here. And you can see that there's the 3 hydrogens are said to form a triangle, but the nitrogen actually, and they're all in the same plane, but the nitrogen is actually in between all of them, but up out of that plane. So we call this molecular geometry Trigonal pyramidal, again a 3-sided pyramid. Now again, the unshared pair here take up a little more space than the bonding pairs, so the HNH bond angles are going to be a little bit less than 109.5 degrees, and they're about 107 degrees. The third possibility for 4 electron domains is something like water. Now water has 2, again, so we've got 4 electron domains. We have 2 bond pairs and we have 2 unshared pairs. And so let's bust out that shape. So it's going to look something like this. And what shape does that molecule look like? Does it look like something we've seen before, like in the last couple minutes? Hopefully that answer is yes. And so that molecular geometry is bent. So for 4 electron domains, the electron pair geometry, or the electronic geometry, always tetrahedral. And you've got 3 possibilities for the molecular geometry. And I want you to see if you can see the pattern here. When is the molecular geometry and the electronic geometry, when are they the same? All right, so if you have time to think about this. So the molecular and the electronic geometries are the same when there are no unshared electron pairs on the central atom. And when they become different, in the case of ammonia and water here, when there are unshared electron pairs present. All right, next up, 5 electron domains. Oh, but before that, I always forget about that. So here you've got 2 larger unshared electron pairs, and which means that they push down even more on the shared pairs. So that angle is actually even a little bit less. It's 145.5 degrees. And I think at this point it would be useful to show you how to draw these with some perspective, and there is a convention for that. So to black. And I'm going to use the ammonia as an example. So in a tetrahedral structure, you can get there's going to be 5 things, right? In this case, it's the 4 atoms and the unshared pair. So there are 5 things, and 3 of them can be defined to be in any one plane. So in this case, I'm going to say that, and they're kind of like this. And I'm going to say that one of these is the unshared electron pair, and here's the other hydrogen. So that would be these guys right here. So what about those? So the hydrogen kind of in the back is going down into the back. So the way that we show that with some perspective is you kind of draw this dash wedge. It gets smaller as it goes out. So that's telling you that hydrogen is coming down and going into the screen. And the way you show perspective for coming out towards you is a solid wedge that gets bigger. So that's kind of the way that we draw this with perspective. All right, next up, 5 electron domains. This one's fun. So the geometry for the electron pairs is going to be a trigonal bipyramidal structure. And the molecular geometry, well, it kind of depends. So for 5 bonding pairs, so PCl5 is an example of this. The Lewis structure looks like this. It's all single bonds. There's an expanded octet. The phosphorus has 10 electrons on it, but you know, it's a third row element. That is fine. And shown with perspective, it kind of looks like this. So let me describe the structure here a little bit for you. So still drawing here. You know, so you've got 3. These 4 atoms here are all in the same plane, the plane of the screen. And these 3 chlorines and the phosphorus are also all coplanar, and that plane would be like parallel to the floor. So again, because there aren't any unshared electron pairs, this molecular shape is also a trigonal bipyramidal shape. And I don't know if the faces actually do you much good with that. But there's an important distinction for this trigonal bipyramidal shape. All the positions aren't equivalent. So these chlorines, the ones that go above and below the triangle plane, for lack of a better term, are called the axial positions. The 3 that form the equilateral triangle are called equatorial positions, and they are not the same. And I want to show you that. All right, so here's, I think, the best way to convince yourself that the positions aren't all equivalent. So the green ones are the equatorial positions and the purple ones are the axial positions. So let's look down one of the axial bonds. What do you see? You see the 2, one of the equatorial bonds. What do you see? You see the 2 axial bonds at 90 degrees and the other 2 equatorial bonds at 120 degrees. If you look down one of the axial bonds, you see the 3 equatorial positions at 90 degrees and the other axial position at 180 degrees. So why is this important? It's important for if there's an unshared pair. Remember that we said that unshared pairs take up a little more space. So what I want you to do is take a second, pause if you need to, try to figure out which position actually has more space, which is more spacious, the axial ones, the green ones, or the equatorial positions. All right, and remember your answer, and let's see what it is. So